Let's add a little bit more to this marine heat wave dynamics. Some schematics of how these heat waves can get formed and what processes may allow us to predict them at what time scale can be looked at with the couple of review papers that appeared that I'm referencing next. So as I said before, once a heat wave is defined as 95th percentile based on any season or the warm season and so on, you can go back and retrofit the past temperature variabilities into heat waves, but I prefer to look at conditions where ecological damages were observed and there was definitely impacts, but nonetheless this definition is not very strict. So here are some examples. This is Rose abalone damage. This is the main lobster, and these are called Cassin's auklets, found off of British Columbia and northwest US, little birds that are getting affected by the heat wave. So that's the region with the so-called blob that we talked about in the Gulf of Alaska, coming down to the coasts of Oregon, Washington, California current, and so on. The two papers provide some schematics of how mixed layer temperature anomalies can be generated. We have briefly discussed geostrophic currents, where if you're away from friction in the middle of the ocean, let's say, and away from the surface or near the surface where wind effects are separately treated with Ekman currents like this, then the balance between Coriolis and pressure gradients gives us geostrophic currents, and they can advect in heat and affect the mixed layer temperature. So you can change the mixed layer temperature by either changing the depth, typically making it shallower. You can warm it if other conditions like heat fluxes remain the same and the entrainment is reduced, and so on and so forth. And you can get it also through mixing, like mesoscale mixing. In this case it's a anticyclone, so you can see that it's a converging. If you in the northern hemisphere, if you put in your Coriolis effect, this is going to be a converging eddy, which is going to converge surface warm waters to create mixed layer changes and sea surface temperature changes. You can have Ekman advection, which is wind driven currents, and of course you can have turbulent flux anomalies at the surface. So you have radiative heat fluxes like short wave and long wave, which are typically the largest components. Of course you can also have sensible heat fluxes, as we will see in a minute, and depending on the depth of the mixed layer you can also have the shortwave penetrating and escaping from the bottom of the mixed layer, called here as outgoing shortwave, or it's often called penetrative radiation, and you can have changes in upwelling and downwelling as well. So generically speaking, those are the processes that drive changes in mixed layer depth and sea surface temperature and the heat content, which is what we are looking at in this case. Let's say we have a background state like this with latitude and latitude and longitude, with the sea surface temperature gradient here, and the background state or the climatology or a given seasonal mean state may look like this, and then some perturbation happens because of winds and heat fluxes, which begins to push the warm waters into the colder regions. So presumably the ecosystem here is used to these background states, but you have created anomalies in sea surface temperature and currents and associated winds there. So this is not something, depending on how quickly it gets established, how quickly it grows and so on, the ecosystem may not have time to adjust, or there may be species that cannot always move as fast as the heat content increase happens. So associated with that, you can have background heat flux and winds. So there is a background mixed layer depth with the temperature, and then you have perturbed states to the wind speed. Wind speed can decrease and reduce latent heat loss, for example, and create a shallower mixed layer depth and increased sea surface temperatures like this. So you can see the anomalies in heat flux and winds, and then resulting temperature anomalies and mixed layer depth anomaly with warmer temperatures near the surface, cooler temperatures below. And this obviously can have not just ecological consequences directly for the upper trophic levels like small fish, big fish, and so on, but also change nutrient supply, primary production. So you can also affect food supply to the smaller fish. So forage fish can be reduced, so the top predators can be affected. So you have this cascade of events depending on how long it lasts, for example. And another way to look at this with this paper here is looking at a coastal region. So there is a coastal upwelling indicated here, and the weather system, something like a atmospheric high pressure blocking system, is shown. So favorable synoptic systems like a high pressure system is sitting here. If you have high pressure, typically you have low rainfall, reduced cloud cover, so you can have increased radiation, solar radiation coming in. Winds will be weaker typically. Low pressure, bad weather, clouds, rain, etc. High pressure, nice weather, low clouds, weak winds, and so on. So you can have reduced latent and sensible heat fluxes and drive enhanced warm water advection through surface Ekman transport, as we talked about. So you can make the mix layer shallower by suppressed vertical mixing, because you have reduced the turbulent kinetic energy of the winds, and you have stabilized the surface by increased heating, reduced heat loss. So you have reduced upward Ekman pumping and reduced enhanced warm water advection through the large scale circulation. So these are just kind of schematics explaining the processes that can drive changes in heat content near the surface and create marine heat waves and affect ecosystems, right? So of course gas exchanges can also be affected by these things, and there are climate drivers that can occur like El Nino Madden-Julian oscillation, which is an intraseasonal time scale process, North Atlantic oscillation, which is typically a lower frequency thing, interdecadal Pacific oscillation, which is a very low frequency thing, monsoons, which are seasonal, and you have on top anthropogenic warming, which is a trend scale on multi-decadal time scales. All these things can have remote atmospheric teleconnections through so-called Rossby waves, which we haven't discussed in detail, but these are waves created because the Coriolis effect changes with latitude. Remember, for waves you need a perturbation force and a restoring force. For Rossby waves, perturbation can be diabatic heating, wind stress curl, and so on. Adiabatic heating in the atmosphere, wind stress curl in the ocean, or reflected energy from the coasts, and so on. During El Nino, typically you have Rossby waves from wind forcing. So for Rossby waves, the restoring force is the planetary vorticity, or the Coriolis effect, dependence on latitude. Okay, water circulation is of course the rising air in the West Pacific sinking in the East Pacific during El Nino. This is perturbed, which obviously creates warm waters in the east, reduced upwelling, reduced photosynthesis, and so on. So reduced primary production. So megafauna and bird mortalities are well known. Harmful algal blooms happen whenever you have typically warming, because they can compete better for the limited amount of nutrients. For example, you can have coral bleaching, species range shifts, and tropicalization when the waves associated with El Nino can propagate all the way up the Central American and North American coast into Gulf of Alaska, for example. You have altered community structure, coastal fishery impacts, shellfish aquaculture closures, dieback of kelp forests, seagrass habitat loss, and so on. So the big fish that can move when there are such perturbations, but these bottom dwellers cannot move, so there is often mass mortalities, and small fish can also die, and the birds that feed on them will face issues as well. So we are taking processes at various time scales, which means the heat content changes and sea surface temperature changes also happen at various time scales, from intra-seasonal to intra-annual and decadal time scales. But that gives you a sense of where the potential predictability will come from at various lead times, and what the scales of those things and potential would be. So specific heat waves are used here. I haven't shown a map, but you can find a map in this paper as well. So West Australian heat wave in 2011, Northeast Pacific and Southwest Atlantic, Eastern Tasmanian Sea, Tasman Sea, and heat spikes and so on. And I won't read all the details, but there are predictability lead times from months, weeks, seasons in ahead to years and days, and predictability source can be local or remote climate forcing like Rossby waves or Kelvin waves, can be atmospheric preconditioning and or teleconnections like El Nino related Walker circulation changes or Indian Ocean dipole or Atlantic Nino, oceanic preconditions and or teleconnections which precede El Nino, for example, transitory weather or eddies, which is very common, especially in the Pacific warm blob region. So persistence of these heat waves can be months, sometimes hours to days. Vertical scale can be 100 meters, tens of meters, hundreds of meters, and so on. Horizontal scales can be thousands of kilometers, or hundreds of kilometers, or very local. And impacted ecosystems can be surface or to benthic within the mixed layer, so upper layer where there is often photosynthesis happening, surface to benthic, and minimal here. Impacts can be potentially substantial, moderate to substantial, or minor, and the conditions associated with them can be strong atmospheric and oceanic contributions, strong atmospheric and weak oceanic contributions for these specific cases, weak atmospheric and strong oceanic conditions, weak atmospheric and oceanic contributions, and so on. So again, these are specific events that were identified. Some ecological impacts were also identified, so these are worth looking at, especially in terms of whether they can be predicted, so that some preventive actions may be taken, and so on. So this is a more broad schematic showing marine heat wave potential predictability and forecast time scales. So at short time scales, it is an initial value problem, so that you initialize the ocean and give it the winds, let's say from a weather forecast or a seasonal climate forecast, and keep integrating. But as you go to longer time scales, like seasons to years to decades, they become what are called externally forced. In other words, ocean response itself to the changing climate becomes important, and it's not an initial value problem anymore. We haven't gone into these details, but I have other courses where you can find such details. So here it is broadly saying there are deterministic forecasts in these time scales, which means you are actually running, let's say, a dynamic model and saying how the evolution is going to happen on days or seasons, depending on what is the predictability. Or you are doing statistical forecasts, typically going to something like anthropogenic climate or decadal forecasts. So these are not projections, these are predictions, which are technically they are different. So initialized integrations into the future, either done statistically or with dynamic models. So again, here you have atmospheric oceanic weather forecasts giving you these. So forecasts of atmospheric blocking, coral bleaching, and ocean eddies are possible from days out to month to weeks. Ocean state re-emergence, so mixed layer is deep at some point, and then it shallows. Next winter, let's say next season it can deepen again and take the anomaly that was left behind in the previous season or the previous year, and so on. So these can occur via known evolution from observed ocean states as initial value problems. So these can be the blob off of northwest US, for example. Seasonal forecasts of coupled models like ENSO, Indian Ocean Dipole, Atlantic Nino, and so on, and teleconnections from ENSO and other climate models. So atmosphere via changes in water circulation or extratropical wave trains. So here South Pacific marine heat wave and South Atlantic marine heat waves are example. Oceanic Kelvin waves as opposed to Rossby waves. These are gravity waves. So the restoring force is gravity. So because there is buoyancy and stratification in the ocean, if the water parcel is moved up or down, buoyancy can restore it. So that's gravity. So you can again have various time scales of predictability, and this example here is Ningaloo Nino, which is off the west coast of Australia, which has seen some heat waves in the past decades. So these can be predictable because of wave pathways from wind-driven ocean perturbations. So oceanic Rossby waves again, and decadal forecasts can be done with climate models. Is gone into the statistical range here because as far as we know there is no predictability at these time scales, but some empirical mode approaches can be taken to make statistical forecasts. So these are via predictable climate variability and forced changes in background state. We are not going into details, but just try to get a sense of it. And of course, anthropogenic climate change, which can go into decades and centuries. And here, these are decadal forecasts, of course, going from years into decades. So these are via forced changes in background state and variability. Okay, so I just wanted to include these to give a little bit more sense about the marine heat waves, especially starting with observed impacts and looking at specific events and see how they were formed, processes involved, and potential predictabilities in them, so that future action is possible. It's not always possible to prevent some events like chloral bleaching when large-scale events are converging to create marine heat waves, but nonetheless having predictions potentially can lead to some actions in the future, but having predictions is good enough, very good anyways. Okay, so let me leave it here.